Let's begin with the first application of Ampere's law, a system of a solenoid. A solenoid is designed to produce a magnetic field of 0.2 Tesla at the center. The wire can carry a maximum current of 10 ampere. What is the minimum number of turns per unit length the solenoid must have? So let's assume the number of turns itself is capital N, and the length of the solenoid is capital L. And this solenoid carries a current I, which we know to be 10 ampere. So the red arrows in the axis of the solenoid is the magnetic field, and it's heading in the leftward direction as shown by that arrow due to the direction of the current, and we get the direction of the magnetic field from the right-hand rule as we discussed in our previous video. Previously, we have determined the expression for the magnetic field for a system of solenoid shown here. It is quite simply the permeability of free space times the electric current times the number of turns per unit length. Note, this little n here is the number of turns over the length of the solenoid. What we are interested is the minimum number of turns per unit length, namely the minimum value for this little n given a maximum value for this current. Rearranging the terms and solving for n, we get magnetic field over mu naught I. So when I is maximum, then n is minimum. So let's substitute the given data. Magnetic field is 0.2 Tesla. Mu naught is 4 pi times 10 to the power minus 7 Tesla meter per ampere. And the current itself is 10 ampere. And this results in 15,915 turns per meter. And that's the answer. Let's look at another application of how to use Ampere's law. You have a long solid conductor with a radius A. So that is the central conductor shown in yellow right there, the radius of which is A. And this conductor is fixed on the axis of a tube with inner radius B and outer radius D. So you have this blue color hollow tube with inner radius B and external radius D. The central conductor, that's this one right there, and the tube, that's right there, carries equal currents in opposite directions. So the yellow conductor carries current in that direction to the right, and the external tube carries current, the same amount of current, but in an opposite direction. Find the magnitude of the magnetic field at points between A and B. That means this region right here, the region between the solid conductor and the tube, and at points outside the tube, meaning in this region right there. So let's start with part A. Note that Ampere's law states the following expression: I enclosed. Now when we say I enclosed, this is the current enclosed within the contour C. So within this region, the magnetic field is circular. We know that. It's closed loop like that. And the direction of the magnetic field given this current in that direction, according to the right-hand rule, is going that way. And we should take the contour C to coincide with the magnetic field. That's what we learned in our previous video. Now let's assume that we are looking at a magnetic field at some distance r from the center. So everywhere on that circle, a distance r from the center, namely on that circle, on that contour right there, B is a constant. and the direction of B and dl are the same. So if you have the magnetic field going like that, so that at one particular point, let's say here, the magnetic field is heading that way, and dl also heading that way. It is an element vector. So that means this integral will simply becomes that. And you can take the b outside because it is a constant. And the integral becomes that. Now, since b is a constant and this integral is none other than the circumference of this green contour, it is quite simply 2 pi r. So putting everything together in this expression, we get b 2 pi r equals mu naught and the current enclosed. The current enclosed by this contour C is just this current that belongs to the central conductor. So it is just capital I. And solving for the magnetic field, you get mu naught current over 2 pi r. So as long as r is in between A and B, the magnetic field is given by this expression. Now, part B. Part B asks you to determine the magnetic field outside the hollow conductor. So the contour would look something like this. So let's assume there exists a magnetic field and the contour is C. So rewriting Ampere's law, we get an expression like that. Mu naught current enclosed. Note that now this contour C is this green circle right there. Before proceeding, let's look at the right-hand side of this Ampere's law. Let's determine what the current enclosed by that contour is. So there are two currents enclosed by this green contour. One is I that belongs to the central conductor, the yellow conductor, and the other one is the current in the equal amount but in opposite direction that flows on the hollow circular tube outside. What that means is that the current enclosed by that contour is quite simply I plus minus I. So if you take this I to be positive, then this I has got to be negative, and the net current enclosed is quite simply 0. So the current enclosed term is 0. That means there is no magnetic field. So the magnetic field is 0 at all points outside the system. Problem 3. Figure below shows an end view or cross-sectional view of two long parallel wires perpendicular to the xy plane. So this is the xy plane, the computer screen. So this is wire 1 and this is wire 2. And both these wires carrying current into the plane as indicated by the two crosses. They carry the same amount of current into this plane. So both of the currents are in the same direction. So this is 2 ampere and this is 2 ampere. Calculate the magnetic field at this point, which is 8 cm away from the origin on the x-axis. The first thing we have to realize is the magnetic field at point Q is produced by two sources. The first source is this current and the second source is that current. So we have to compute the contributions separately. Let's do the upper current. The magnetic field due to the upper current. Note this is just an approximate sketch. So at this point Q, the magnetic field due to this current will be heading in that direction because the entire field is going in a clockwise direction due to the direction of current going into the plane. Because the magnitude of this magnetic field is given by mu naught. The current is 2 ampere over 2 pi, and the distance from here to there, according to Pythagoras' theorem, is 10 centimeters or 0.1 meter, because this is 6 This distance is 8 cm, so this has got to be 10 cm or 0.1 meter. Next, let's look at the magnetic field of the lower current, how it looked like. The magnetic field due to this lower current is sketched in purple. The direction of that magnetic field is also going clockwise due to the fact that this current is going into the plane. According to the right-hand rule, this is the direction of the magnetic field. And at point Q, that means the direction of magnetic field is going like that. We note that these sketches are approximate. The magnetic field due to the lower current has the same magnitude as the magnetic field due to the upper current. And it's given by mu naught times 2, because the currents are the same, 2 pi, and the distance from the center to here is again 10 centimeters, because that distance is 6, this is 8, so the hypotenuse is 10 cm, or 0.1 meter. What that means is these two arrows have the same length, and their x components are heading in an opposite direction, so the x components will cancel. And the reason is because of the symmetry of the system. They are symmetrical about this line. So only the y components of these two magnetic fields would survive, and they will reinforce each other. And we need to find what is the y component of BU and y component of BLR. And to do that, we need to know this angle. Let's call that alpha. It's the same angle, alpha. So what that means is the total magnetic field is quite simply BU plus BL times cosine alpha, because we are only interested in the y component, and only the y component survives. Since we are interested now in calculating cosine alpha, let's just look at the green circle, extending this arrow on the other side just to make things a little bit simple. You see that this angle is also alpha, because this is a tangent line, so this one is 90 minus alpha. That would make this angle alpha. So what that means is cosine alpha is quite simply 0.8. That is this length over that length, because this is a right angle triangle. Substituting this information, and this information into this expression, we get the following for the total field. So the total field, which is in the direction of negative y-axis, is given by this plus this. They're essentially the same term. So you're going to get mu naught 4 over 2 pi times 0.1 times cosine alpha, which is 0.8, which will give us 16 mu naught over pi Tesla. So that is the magnetic field at this point Q due to these two currents. And the direction of this net magnetic field at point Q is along the negative y-axis. That solves the problem. If you find this video useful, please like and subscribe for notifications on more future videos. Thank you for watching.